Hello, my name is Pramod Chundury. I'm a PhD student affiliated with the Human Computer Interaction Lab at the University of Maryland. I'll be presenting results from a design study that we conducted for making charts accessible for blind individuals on touchscreen devices. This work was done in collaboration with Yasmin Reyazuddin, Dr. Bern, Dr. Jonathan Lazar, and Dr. Niklas Elmqvist. The data visualization research community continues to make tremendous progress to help individuals make important data-driven decisions. But visualizations are largely inaccessible for about 285 million people with visual impairments and 39 million blind individuals worldwide. With growing research in the visualization community, the barriers for entry to understanding data and charts are widening because of the limited focus on accessibility. Sensory substitution is a common technique used to help individuals overcome vision challenges and provide better access to information. It's the idea of transforming visual stimuli to other sensory modalities such as touch, hearing, and even smell. In our study, we explore how to effectively employ sensory substitution to support visualization-related tasks on touchscreen devices. Our work explores the idea of multimodal chart accessibility for touchscreens. We use touchscreen interactions for direct manipulation of chart elements, and the output is a combination of non-speech sounds or tones and speech output. Let's briefly take a look at some of the various approaches to making charts accessible. Many blind people use screen readers to translate text on screen to voice that they can listen to, often just using their smartphones and tablets. Research shows that creating alternative text and captions for charts are effective to communicate data narratives via screen readers. Captions work well with screen readers, but have limitations when using data visualizations or visual representations for data exploration. Sonification and verbalization of data values helps blind individuals through the creation of infosonics and audio narratives. However, these solutions rely on serial access to data, mostly because both narratives and sonification require the listener to wait till the end of the audio playback to understand the data trends. Touch is another powerful sense for physicalizing data and has also been explored in the research communities. Refreshable braille displays and tactile graphics are examples of conveying information using the sense of touch. Tactile graphics are often used by teachers of people with visual impairments in classroom settings. Using a haptic display, Dausch and colleagues explored making Microsoft Excel charts accessible using vibrations and sound. Such solutions often require specialized, expensive hardware and also have challenges when scaling to large data volumes. Zhao created iSonic, a tool that used non-speech audio to convey data, and explored keyboard and touch interactions, and also developed audio information seeking principles. Similarly, slide tone and tilt tone conveys shape of the data using both sound and touch, but this requires specialized hardware as well. In our work, we attempted to design a method for sensing complex data sets on smartphones and tablets using touch-based exploration and by using off-the-shelf hardware. Cross-modal sensory substitution is the idea of replacing in real time the output for one sensory system with the output for another sensory system. For example, in our work, touching the chart canvas would produce audio as the primary output, as opposed to the meaning being encoded to the haptic feedback on touching the touchscreen. We first conducted 3 design sessions with our collaborator. She is blind and familiar with scatter plots and other statistics, and had also had to interact with other visualizations as part of her graduate school work. The first 2 workshops were for 2 hours and the last one was for 3 hours. In the first session, we explored tactile scatter plots printed on thermoform paper. In the second session, we focused on testing the sound design of our TactualPlot system, which was implemented on an iPad, and the touchscreen logging capabilities of the device as well. In the last session, we explored 3 different visualization tasks on both tactile scatter plots and our TactualPlot system. Next, we conducted design reviews of the TactualPlot system with 2 experts. Expert 1 was familiar with charts and provided feedback on the technique itself in the context of graphical perception. She was also deafblind. R2, or Expert 2, was a braille proofreader and is an expert at consuming information in the tactile form. We generated 12 bivariate datasets for the design sessions. We control the spatial structure of the scatter plot by varying the data scatter, the data volume, and the direction of the linear trend. We adopted scatterplot tasks from past literature. For example, a trend task to gauge the presence and direction of a linear trend, and a numerosity task to understand how many points there are in a specific region. We collected touchscreen logs, qualitative feedback, screen recordings, and observation notes from all the sessions. Our TactualPlot system was implemented on an iPad using open source web frameworks for audio and for touch capabilities. The system has 5 primary touch areas: the chart title at the top of the chart, the y-axis or the vertical axis on the left edge, the x-axis or horizontal axis at the bottom edge, the sonification or audio legend on the right side of the screen, and the chart canvas is in the region in the middle where all the data points are spatialized. In our current implementation, users can interact with scatter plots using discrete and continuous touch gestures. Discrete gestures such as tapping would produce speech output that verbalizes data and chart elements. For example, tapping on a tick mark on the left edge will verbalize the corresponding axis value. Continuous gestures such as dragging the finger along the screen would produce non-speech sounds. For example, as a user is dragging their finger, the point density under their finger is mapped to a pitch value in the sound domain. Let's briefly look at a demo of TactualPlot in action. What you're seeing right now is the interface of our TactualPlot system. We have visualized a scatter plot that has 50 points, has a medium scatter and a negative trend. Users can touch the display and drag their fingers around to trigger the non-speech sounds, and tapping gestures will verbalize the data density or tick mark value under the finger. The position of each finger touching the screen is tracked by a circle. When more than one finger is touching the display, multiple circles are shown, and the iPad supports up to 10 fingers concurrently interacting with the screen. So now let's see how the sound works. The point density under the finger, or in other words, the number of data points that are touched, is mapped to the notes of a C major scale. For example, now let's look at how one can start in the origin and move laterally from left to right to sample the sounds.
Origin 0, 0.
As you pan from left to right, the audio is channeled using stereo sound to either the left ear or the right ear based on the location of the finger, as being less or greater than a mid value in the domain. What we saw was that as each finger was moving and sampling points, the pitch of the note changes. The note is played for a few seconds, and if there's no movement, the sound stops. Users can also use the tap gesture to verbalize the point density as they pan, and try to understand the data distribution using a combination
Origin
of taps
0,
and panning.
0. 1, 2, 2, 3, 3, 2, 1, 1, 1, 3.
We visualized the touch position from Design Workshop 3 and found some interesting exploration strategies. In both the images on the slide, the frame on the left shows a snapshot of an initial point in the exploration, and the frame on the right shows the touch trail at the end of the exploration. As you can see, our collaborators started exploration at the origin with both fingers on the touchscreen and chose to explore either laterally or vertically. Through such visual analysis, we were able to understand how a particular region was sampled for a particular task. We compared TactualPlot exploration strategies with tactile graphics, and we conclude our work by discussing future expansion of our design space and the TactualPlot system. Please read our paper for more information. We are currently working on expanding TactualPlot to support scatter plots, line charts, bar charts, and pie charts. This includes an improvement to the sound design of the system through personalizable sound parameters. Also, we are currently preparing to analyze more touchscreen log data as part of a larger quantitative evaluation of the system and the technique itself. Thanks for listening.